So here you understood now here then how we are calculating the area here. So here this is we are calculated here yeah, how we are calculating the area means 22 into 28. Hope you understood here why we how we got the 28 here instead of 33. That is ignoring 3 and 3 lambda and minus of 1 here, because 1 lambda we are using in the VSS and 0.5 in the VDD and 0.5 in the VSS here. Hence finally we have got the length into width, and why it is 2 here, why we are using multiplying with the 2, nothing but as it is a non-inverting, we have two circuits here. We have two pairs of NMOS as well as the inverter, hence multiplied by 2 we have got the 1200 lambda square here. If the lambda means what is the technology we are using, if we are using the 2.5 micrometer technology, then multiply this one here, so we are going to get around this value here, that is 7500 micrometer here. So here what is the meaning of this one means, so to store 1 bit here, okay, this much area it is where it is taking here, that is 7500 micrometer it is taking to store the 1 bit of data, just to store the 1 bit of 1, or it may be 0 here, whatever we call it as a bit here. So in order to store this data it is taking this much area here. Okay, similarly we can this is for NMOS, with respect to NMOS we have discussed here. Okay, similarly we can go for a CMOS also. So here you can see here the same thing discussed in the text also. So 22 into 28 into 2 here, so this is the value. Area per bit means here to in order to store 1 bit of data, this much area is required here. Okay, and when we this is for NMOS, whatever we have discussed, no, it is about the NMOS here. Similarly for a CMOS also, here this 28, this value remains same here, that is the length remains same, the width is 38 here. Okay, you understand the value how we got the 28, so the same quite it is same here also, the width only here it is increased to 38 lambda here. So multiplied by 2 once again, why it is so means two pairs of NMOS and inverter we have used. It is a non-inverted dynamic register here, hence we are using the multiplied by 2 here. So finally we got this much area here. So for the for example, if the lambda, that is the technology, if we are using the 2.5 micrometer, then 1300 micrometer square, this much area it is taking to store a 1 bit of data here. Okay, so in this much area it is taking to store a 1 bit of data. So they have given here such area requirement would result in a maximum number of bits stored on a 4x4 chip area, which is approximately equal to 1.2 kilobits here. So what is the meaning of this sentence means, here if you are taking, okay, to store 1 bit, this is the area it is using, right? So this much area it is taking here. In case if they give 4x4 millimeter, okay, this is the area, 4x4 nothing but it is the area here. Sorry, okay, let us make like this is a 4x4 only here. Okay, so 4x4 nothing but for this area how many bits it can store, very simple here. So for 1 bit, how much it is taking here, 1300, right? 1300 it is taking for 1 bit. Okay, for this much area, that is 4x4, how many bits it will take? So cross multiply here and you will get a value here. So this area they have given here, for 1 bit this much area it is taking, for this much area how many bits it is taking, that is what the calculation they have made here. So you can calculate and see it is approximately around 1.2 kilobits. So in the 4x4 millimeter of chip here it is storing to 1.2 kilobits here. Okay, this is the calculation of the area for NMOS and the CMOS here. Okay, that too for a dynamic shift register. Okay, thank you. So So next we go for a dissipation here. Okay, in the dissipation we calculate for a here this also here. So dynamic power consumption, that is switching dissipation, sorry here now. So here what is the dissipation type means switching dissipation will be significant to calculate here. Okay, so the dynamic power consumption here PD is given by M into CL VDD square into F here, where M is the duty cycle, CL is effective load capacitance, and F is the clock frequency. Okay, for the NMOS here, okay, first we are looking into the NMOS. What we are exactly calculating means how much power it dissipates when we store a 1 bit of data here. Okay, how much power a static dissipation takes place when we store a 1 bit of data. Okay, so here the calculation goes here like this here. So here this is a pull up and a pull down here. Okay, the ZPU and ZPD, we know already all these terms here. So pull up circuit and a pull down circuits here. So pull up is given by 4 into RS here. What is the RS here? In the second module already we come across the sheet resistance calculations here. What is sheet resistance and all. So here the for a pull up it is a 4:1, right? Hence 4 into RS here. Okay, so what is the RS value here? RS value is 10 raised to 4. So already I have mentioned here RS value here. Okay, for pull down, similarly for pull down, what is the ratio here for a pull down here? 1:2 here, right? So it is a 0.5 I am taking. So 1/2 nothing, 0.5 here. Of course RS it remains same into 10 raised to 4 here. Okay, so pull up and pull down, what is Z pull up and Z pull down here. The ratio how we are calculating this here is length into 4:1, nothing but a 4 here into RS. Okay, here for a pull down the ratio is L into W. This is L into W ratio, right? W ratio it is 1:2 here for a pull down here. So hence 1/2 here, 0.5 I am taking. Of course RS value remains in 10 raised to 4 here. So here current, let us calculate the current first here so that we can calculate the power dissipation. So what is the current? How we are giving the current here? VDD by here impedance here. Okay, so what is the impedance we calculate for a pull up and a pull down here? So pull up is a 4 and pull down is a 0.5 here. So 4.5 into 10 raised to 4, this is the RS value. This 10 raised to 4 is the RS value. So VDD is 5. I think they have taken wrong here. Okay, this is wrong here. So VDD is 5 volts and the impedance is 4.5 into 10 raised to 4. So when we calculate, we got the current value here. So static dissipation, next to calculate the power here, static dissipation per bit stored is equal to VDD power. We are very simple calculation. Power is equal to VDD into current. So VDD is 5 here and current we have calculated. So this much power. Okay, finally, sorry. So this is the power it is taking in order dissipating in order to store a 1 bit of data here. So in order to store a 1 bit of data, this much power is getting dissipated. So we have calculated 4 cross 4, so this many 2.1 kilobytes. Okay, it stores here. So similarly here also there's 2.1 kilobits on a single chip should would dissipate. How much it is dissipating? This is for 1 bit, for 2.1, so just multiply these values, that's it. So finally it is dissipating 1.15 watts here. Okay, that much power is getting dissipated in whenever we store a 2.1 kilobits of data here. Okay, so next is volatility here. What is the volatility here? Nothing but data is stored by the charge on the gate capacitance of each inverter stage. So the data storage time is less than 1 millisecond. So here I have shown the diagram here. So here in the inverter, so this is the NMOS and this is the inverter. Here we have a capacitance, gate capacitance. Maximum it can store without refresh operation, it can store up for a 1 millisecond. Hardly it can, or less also, it can store up to 1 millisecond. Whatever the, for example, data, 1 bit is there, so it can store this 1. Here let us go for a next topic here, volatility here. So what is that volatility here is, so whatever the data here, this is a CG here, we call it as a gate capacitance here. Okay, this we call it as a gate capacitance. Already we have seen this also in second module. Okay, between like this NMOS and the inverter, we have a gate capacitance where data has been stored here. So let us consider sorry. So let us consider bit 1. Okay, it has been stored, I mean one bit has been stored here. So maximum it can store that one bit up, the timing, how much maximum time it can store is 1 millisecond. That's it. Within 1 millisecond we need to refresh it, else data leakage takes place here. Okay, that is what the meaning of a volatility here. So maximum time data can be stored in the gate capacitance is 1 millisecond or less than that also. Okay, later if you don't refresh here, okay, then data may leak here. Okay, that refresh operation is important here in order to have to get back the to maintain our data here.